Hello everyone, I am Abhijit Lal, Assistant Professor, Department of EEE, BIT Durg. Today we are going to study about earth resistance for different installations. So this will be the contents for today's lecture. So let's start with earth resistivity. The term earth resistivity expressed in ohm centimeters is one basic variable affecting resistance to earth of an electrode system. Earth resistivity measurements can be used conveniently for geophysical prospecting to locate ore bodies, clays and water bearing gravel beneath the earth's surface. The measurement can also be used to determine depth to bedrock and thickness of glacial drift. Measurements of earth resistivity are useful also for finding the best location and depth for low resistance electrodes. Such studies are made, for example, when a new electrical unit is being constructed, a generating station or substation, transmission tower or telephone central office. Also, earth resistivity may be used to indicate the degree of corrosion to be expected in underground pipelines for water, oil, gas, gasoline, etc. Now let us discuss how earth resistivity is measured. A 4-terminal instrument is used to measure earth resistivity. It uses 4 small-sized electrodes driven down to the same depth and equal distances apart in a straight line as shown in figure below. Here we can see there are 4 electrodes, that is C1, C2 and P1 and P2. So this method is called as 4-terminal method of measuring earth resistivity. 4 separate lead wires connect the electrodes to the 4 terminals on the instrument as shown in the figure. Hence, the name of this test is called the 4-terminal method. Dr. Frank Werner of the US Bureau of Standards, now it is NIST, developed the theory behind this test in 1915. He showed that if the electrode depth, which is denoted by capital B, is kept small compared to the distance between the electrodes, which is denoted by capital A, then the following formula applies, that is rho is equal to 2 pi AR, where rho is the average soil resistivity to depth A in ohm centimeter, pi is the constant, that is 3.14, A is the distance between the electrodes in centimeter, and capital R is the mega earth tester reading in ohms. For example, if the distance A between the electrodes is 4 feet, you obtain the average earth resistivity to a depth of 4 feet as follows. First, convert the 4 feet to centimeters to obtain capital A in the formula, that is 4 into 12 into 2.54 centimeter, it will be equal to 122 centimeter. Next, multiply 2 pi A to obtain a constant for a given test setup, that is 2 into 3.14 into 122, it will give you 766. Now, if instrument reading is 60 ohm, the earth resistivity would be 60 into 766, or it will be equal to 45,960 ohm centimeter. Now let us discuss how type of soil affects resistivity. Whether a soil is largely clay or very sandy can change the earth resistivity. The following figure shows the deeper earth electrodes lower the resistance. The graph show the relation between character of soil and resistance of driven electrode at increased depths. So the figure shows that as the depth of the electrode changes, the resistivity also changes. Next, the following table shows the resistivities of different soils. So first is the fills under which comes the ashes, cinders, brine waste. Its average resistivity is 2370 ohm centimeter, minimum resistivity is 590 and maximum is 7000 ohm centimeter. For clay such as shale, gumbo, loam, the average resistivity is 4060 ohm centimeter. The minimum resistivity is 340 and the maximum resistivity is 16,300 ohm centimeter. Next is varying properties of sand and gravel. For this, the average resistivity is 15,800, the minimum resistivity is 1020 and maximum resistivity is 1,35,000. Last is the gravel, sand, stones with little clay or loam. Its average resistivity is 94,000, minimum resistivity is 59,000 and maximum resistivity is 4,58,000. Next is the effect of moisture and dissolved salts on resistivity. So, in soil, conduction of current is largely electrolytic. Therefore, the amount of moisture and salt content of soil radically affects its resistivity. The amount of water in the soil varies, of course, with the weather, time of year, nature of subsoil and depth of the permanent water table. Pure water has an infinitely high resistivity. Naturally occurring salts in the earth dissolved in water lower the resistivity. Now, the following table shows the effect of moisture content on earth resistivity. So, the moisture content, if it is 0%, then at the top of the soil the resistivity is 1000 into 10 to the power 6 ohm centimeter, and for the sandy loam it is 1000 into 10 to the power 6 ohm centimeter. And as the percentage of moisture content increases, the resistivity gets decreases. As we can see in the last point, if the moisture content is 30% by weight, then the resistivity for topsoil will be 10,000 ohm centimeter, and for sandy loam it will be 8,000 ohm centimeter. Next table shows the effects of salt content on earth resistivity. Now, the first point shows the 0% by weight of moisture by the added salt. In this, the resistivity will be 10,700 ohm centimeter, and as the salt percent by weight of moisture increases, that is can be seen in the last point, that is 20% by weight, the resistivity gets decreased to 100 ohm centimeter. Now, let us discuss about the effect of temperature on earth resistivity. An increase in temperature will decrease resistivity due to the following reasons. First, the water present in soil mostly determines the resistivity. Second, an increase in temperature markedly decreases the resistivity of water. So, when water in the soil freezes, the resistivity jumps appreciably. Ice has a high resistivity. The resistivity continues to increase and temperatures go below freezing. Now, the next table shows the effect of temperature on earth resistivity. So, for the first point, when the temperature is 20 centigrade or 68 Fahrenheit, the resistivity will be 7,200 ohm centimeter. For 10 centigrade or 50 Fahrenheit, the resistivity is 9,900 ohm centimeter. For 0 centigrade or 32 degree Fahrenheit, that is for water, the resistivity is 13,800, whereas for 0 degree and 32 degree Fahrenheit for ice, the resistivity increases up to 30,000 ohm centimeter. For the temperature minus 5 degree centigrade or 23 degree Fahrenheit, the resistivity increases to 79,000. And lastly, for 15 degree centigrade or 14 degree Fahrenheit, the resistivity increases up to 3,30,000 ohm centimeter. Now, let us discuss the measuring earth resistance for electrical grounding systems. The simplest form of a good ground for an electrical system is a section of iron pipe driven into the earth with a wire conductor connected from the pipe to the electrical circuit. Earth resistivity strongly depends on electrode resistance, as does the depth, size and shape of the electrode. Now, the following figure shows a simplified grounding system in an industrial plant. In this figure, we can clearly see that a lightning rod is placed at the top of the building, which is also called as lightning arrestor, and from that all the equipments are connected, that is the electric motor and all other auxiliary equipments. So the earthing is provided through all these wires and connected to the lightning rod, and it at the end that comes to the earth electrode. The principles and methods of earth resistance testing covered is applied to lightning arrestor installations as well as to other systems that require low resistance ground connections. Such tests are made in power generating stations, electrical distribution systems, industrial plants, and telecommunication systems. A practical earth electrode that provides a low ground resistance is not always easy to obtain. Now let us discuss about the factors that can change minimum earth resistance. So there are 4 factors that can change the earth electrode requirements from year to year. They are as follows. First, a plant or other electrical facility can expand in size. Also, new plants continue to be built larger and larger. Such changes create different needs in the earth electrode. Secondly, as facilities add more modern sensitive computer control equipment, the problems of electrical noise is magnified. Noise that would not affect cruder, older equipment can cause daily problems with new equipment. Next, as more non-metallic pipes and conducts are installed underground, such installations become less and less dependable as effective, low resistance ground connections. In many locations, the water table is gradually falling. In a year or so, earth electrode systems that formerly were effective may end up in dry earth or high resistance. These factors emphasize the importance of a continuous periodic program of earth resistance testing. It is not enough to check the earth resistance only at the time of installation. Now let us discuss about the factors influencing requirements for a good grounding system. In an industrial plant or other facility that requires a grounding system, one or more of the following factors must be carefully considered. The first factor is limiting to definite values the voltage to earth of the entire electrical system. Use of a suitable grounding system can do this by maintaining some point in the circuit at earth potential. Such a grounding system provides these advantages. It limits voltage to which the system to ground insulation is subjected, thereby more definitely fixing the insulation rating. Second advantage is it limits the system to ground or system to frame voltage to values safe for personnel. Third advantage is it provides a relatively stable system with a minimum of transient overvoltages. And lastly, it permits any system fault to ground to be quickly isolated. The following figure shows the typical conditions to be considered in a plant ground system. So here the position of lightning arrestors and the power supply and the insulation fault all are shown in this figure, and these typical conditions should be considered during the grounding system. Second is proper grounding of metallic enclosures and support structures that are part of the electrical system and may be contacted by personnel. Protection against static electricity from friction, protection against direct lightning strokes, protection against induced lightning voltages, providing good grounds for electric process control and communication circuits. Now let us discuss about the nature of an earth electrode. So the resistance to current through an earth electrode actually has 3 components. The first is resistance of the electrode itself and connections to it. Second is contact resistance between the electrode and the soil adjacent to it. And third is resistance of the surrounding earth. So let us discuss about the electrode resistance. Rods, pipes, masses of metal, structures and other devices are commonly used for earth connections. These are usually of sufficient size or cross section that their resistance is a negligible part of the total resistance. Next is electrode earth contact resistance. If the electrode is free from paint or grease and the earth is packed firmly, contact resistance is negligible. Rust on an iron electrode has little or no effect. The iron oxide is readily soaked with water and has less resistance than most soils. But if an iron pipe has rusted through, the part below the break is not effective as a part of the earth electrode. So, the following figure shows the components of earth resistance in an earth electrode. Now, the third point is the resistance of surrounding earth. An electrode driven into earth of uniform resistivity radiates current in all directions as shown in the figure above. So, think of the electrode as being surrounded by shells of earth all of equal thickness as shown in above figure. The earth shell nearest the electrode naturally has the smallest surface area and so offers the greatest resistance. The next earth shell is somewhat larger in area and offers less resistance. Finally, a distance from the electrode will be reached where inclusion of additional earth shells does not add significantly to the resistance of the earth surrounding the electrode. It is this critical volume of soil that determines the effectiveness of the ground electrode and which therefore must be effectively measured in order to make this determination. Ground testing is distinct when compared to more familiar forms of electrical measurement in that it is a volumetric measurement and cannot be treated as a point property. Generally, the resistance of the surrounding earth will be the largest of the three components making up the resistance of a ground connection. Now, let us discuss about the principles involved in earth resistance testing. The resistance to earth of any system of electrodes theoretically can be calculated from formulas based upon the general resistance formula, that is R is equal to rho L by A, where rho is the resistivity of the earth in ohm centimeter, L is the length of the conducting path and A is the cross sectional area of the path. To understand the principle of earth testing, consider the schematic diagram shown below. In this diagram, we can see the three rods, that is rod 1 and rod 2 are fixed and the rod 3 is movable. It is moved between the rod 1 and 2 and a voltmeter is connected between rod 1 and rod 3 and an ammeter is connected between the rod 1 and 2 along with a voltage source. And the second part shows the graph in which the distance and the resistance variation is shown, like how the resistance changes when the distance between the two rods gets changed. As shown in figure 6, with increased distance from an electrode, the earth shells are of greater surface area and therefore of lower resistance. Now assume that three rods are driven into the earth some distance apart and a voltage applied as shown in figure 7a. The current between rods 1 and 2 is measured by an ammeter. The potential difference voltage between rods 1 and 3 is measured by a voltmeter. If rod 3 is located at various points between rods 1 and 2, preferably in a straight line, we can get a series of voltage readings. By Ohm's law, R is equal to E by I, you can determine the earth resistance at any point measured. For example, if the measured voltage E between rods 1 and 3 is 30 volt and the measured current I is 2 ampere, the resistance of the earth R at that point would be 15 ohm. The series of resistance values can be plotted against distance to obtain a curve as shown in figure 7b. Note that as rod 3 is moved away from rod 1, the resistance values increase, but the amount of increase gets less and less until a point is reached where the rate of increase becomes so small that it can almost be considered constant. In the figure 7b, that constant value is 20 ohm. The earth shells between the two rods 1 and 3 have so great a surface area that they add little to the total resistance. Beyond this point, as rod 3 approaches the earth shells of rod 2, resistance gradually picks up, and at near rod 2, the values rise sharply. Now next, let us discuss about basic test methods for earth resistance. So there are three basic methods. First is fall of potential method or three-terminal test. Second is dead earth method, which is also called as two-point test. And third is clamp-on test method. So first test is fall of potential method. So the following figure shows the fall of potential or the three-terminal earth resistance test. In this test, the three rods are used. From the four terminals, we can use either the three terminals or the four. This three-terminal test is the method described previously. With a four-terminal tester, P1 and C1 terminals on the instrument are jumpered and connected to the earth electrode under test. With a three-terminal instrument, connect X to the earth electrode. Although four terminals are necessary for resistivity measurements, the use of either 3 or 4 terminal is largely optional for testing the resistance of an installed electrode. The use of 3 terminals is more convenient because it requires one lead to be connected. Second method is dead earth method, which is also called as two-point test. So the following figure shows the dead end method or two-point earth resistance test. In this, the water pipe system is used along with the electrode. Again, there are 4 points, that is C1, C2, P1 and P2. When using a 4-terminal instrument, P1 and C1 terminals connect to the earth electrode under test. P2 and C2 terminals connect to an all-metallic water pipe system. With a 3-terminal instrument, connect X to the earth electrode and P and C to the pipe system as shown in figure 9. If the water system is extensive, that is covering a large area, its resistance should only be a fraction of an ohm. Take the instrument reading as being the resistance of the electrode under test. The dead earth method is the simplest way to make an earth resistance test. With this method, resistance of two electrodes in series is measured, the driven rod and the water system. There are three important limitations of this method. First is the water pipe system must be extensive enough to have a negligible resistance. Second, the water pipe system must be metallic throughout without any insulating couplings or flanges. And lastly, the earth electrode under test must be far enough away from the water pipe system to be outside its sphere of influence. Now the last method is clamp-on test method. So the following figure shows the basic clamp-on ground testing methodology. The clamp-on ground tester performs a stackless test, which is a ground resistance test performed without disconnecting the ground. Based on Ohm's law, that is R is equal to V by I, the stackless test induces a known voltage in a loop circuit that includes ground, measures resultant current flow and calculates the loop resistance of the circuit. 4-pole earth testers also perform a stackless test. However, they use two clamps, a voltage clamp which is called as V clamp and a current clamp which is called as eye clamp, and keep the clamps separate to prevent interaction between the two. All elements of the loop are measured in series. The method benefits from low return path resistance, that is where the ground resistance is large compared to the effective return loop resistance. Now let us summarize today's lecture. Today we have studied about the earth resistivity, which plays a very important role in selecting the earthing or the grounding system. As we have studied that the earth resistivity depends upon the moisture content and the temperature and also the type of soils. As for different locations, different types of soils are found, and for different types of soil the resistivity will be different. So it is very important before laying the grounding system or selecting the earthing system, the profile of the soil is to be studied and the resistivity of soil to be tested. And we have studied about the different methods in which we have seen the electrodes are used to test the resistivity of the soils, and we have seen a pattern that as the electrodes or the rods gets deeper and deeper, the resistivity gets changing. Next, we have discussed about the effect of moisture and the dissolved salts and their effects in resistivity. As the moisture increases, the resistivity increases, and the moisture content is a very, and as we can say, the moisture content is an enemy to the any earthing system or the grounding system. So the content of the moisture should be limited. Next is the effect of temperature on the resistivity. As the temperature of different locality changes or the soil changes, the resistivity values goes on changing. Next, we have discussed about the methods to determine the earth resistance. That is by using the 3 electrodes. That is the most simple method, and the device used is the Megger for earth resistance. In that method, by using the 3 electrodes, keeping the 2 electrodes at the fixed position and moving one electrode and measuring the voltage and the current, from that the resistance is calculated. So in this way we have discussed different methods to calculate the earth resistance. Thank you.